Hello, and welcome to 1428 online delivery, alternative delivery for March 20th. Today's lecture covers section 4.2. We're going to have two prime learning objectives: graphing polynomial functions and using the intermediate value theorem to determine whether a function has a real zero between two given real numbers. And I do expect you to be able to do these kind of tasks both with and without calculators, so keep that in mind. In addition to the leading term test and finding the zeros of polynomial functions, which we covered in chapter 4.1, it is helpful to consider the following facts when graphing a function. So, if p is a polynomial function of a degree n, then the graph is going to have at most n real zeros. And since a real zero is an x-intercept, it has at most n x-intercepts. And when you talk about turning points, we talked about those as well. It will have at most n minus 1 turning points. And here we talk about what turning points are. Again, turning points on a graph are also called relative max and mins, and these occur when the function changes from increasing to decreasing and vice versa. Now, looking ahead maybe to future studies, there are techniques that are learned in calculus that help students actually identify the specific coordinates of the max and min. In this class, we will only be able to approximate these using our calculators, but we have studied this before, and I will show you how that comes into play in some of the questions that I will likely ask you. Okay, so let's look at the kind of problems we're doing here. I assume that you have done a pre-reading of our section 4.2 for today. And if you haven't, you should do that and then come back and do this. The pre-reading doesn't have to be as thorough as the post-reading. In these problems, what you're supposed to do is identify the maximum number of real zeros, which corresponds to the maximum number of x-intercepts, and talk about the maximum number of turning points that the graph can have. Let's just talk about the odd ones here. So if I go down to problem number 2, I see this is of degree 6. That means it can have up to 6 real zeros, at most 6 real zeros, and that's the number of x-intercepts that it can have as well. And that means since n minus 1 is the number of turning points, it could have 5 turning points. Here, this is a cubic. That means it could have at most 3 real zeros, and it could have 2 turning points. And here is a 4th degree equation, meaning you could have up to at most 4 real zeros, and it's going to have 3 turning points. But there are 2 that have right-handed waves. There is E and there is C, both have right-handed waves being offered, so you have to look at the y-intercept, and in number 12 we're looking for minus 5, and so minus 5 is the y-intercept only on E, so the answer must be E. Now, on many problems in this, when I write a test over a section like this, I ask you to sketch the graph and complete the table for the graph. And so you should plan on saying, oh, this is the way these problems often will be asked. So you do want to sketch as best you can the graph, and you want to be able to answer questions about in behavior, y-intercepts, x-intercepts, and the only way you could do these is if I am letting you use a calculator, but there will be problems where I'm letting you use the calculator, and so you want to be able to find the relative maximum and relative minima. And here's some general advice about graphing a polynomial. So you can determine the in behavior using the leading term test, find the zeros of the function by solving y or f of x equal to 0, and those correspond to the x-intercepts, and you then divide the x-axis into intervals, and you choose test points in each of those intervals to determine the SIGN, the sign of all function values in that interval. You find the y-intercept by plugging in 0 for x, and you can check additional points, and another check is you can say, do I have the right number of turning points? Again, if it's an nth degree polynomial, you can have at most n minus 1 turning points. And remember from the last lecture that we had that the multiplicity of zeros can also be considered as a check, because the graph is going to be tangent to the x-axis if it is even multiplicity. It is going to be crossing the x-axis if it is odd multiplicity. And they also say you can check perhaps with a graphing calculator if one is allowed on that problem. Okay, so here is a suite of problems in your exercises where you to graph the polynomial function, follow the steps outlined. And again, I'm assuming that you've done a bit of pre-reading, so I'm going to invite you to pause the video and you try problem number 17 and start playing the video again when you've completed your work and compare your notes. Okay, so what we can do is we can find the x-intercepts by looking at the roots of this. So we set this y, h of x equal to 0, and this factors nicely. And so we know x equals 0, x equal minus 2, and x equal 2 are roots. So we have that. We also know if we put x to be 0, we get y to be 0 from the equation. And so the y-intercept is 0, 0. I also note that the x equals 0 is a root of multiplicity 3. And this is an odd function because the only powers that we have of the exponents are odd powers, so this is symmetric with respect to the origin. And if you think about the end behavior, that means you're going to have a left-handed wave. Now let's do test points within each of the intervals. So we're plotting these on the real number line. We'll go from negative infinity up to minus 2. We're going to go up to from minus 2 to 0. We're going to go from 0 to 2 and from 2 to positive infinity. We'll pick test values in each of those intervals, and I'll see if I'm negative or positive in each of those intervals, and that tells me whether I am above the x-axis or below the x-axis. Let's put all these things together in our graph, and we find that the end behavior is going down here and it's going up here, so that's our end behavior symbol. The y-intercept was 0, 0, as we can see from the graph. The x-intercepts are minus 2, 0, 0, 0, and 2, 0. And if you use your calculator, and I encourage you to test using your calculator, you remember we have to graph this, but then we look at the left bound, we look at the right bound, and then we enter a guess, and your calculator does the work and tells you what are the coordinates of the relative max in this case and the relative min in the other case. And so that's that. I'm going to ask you to do another one. Why don't you do problem number 25? It is down here. This one is already factored completely for you. So pause this, do your work, and come back and see what the solution is. Pause now. And I am back. Okay, so this is already factored. So we know that the zeros are at x equal 2, x equal minus 1, and x equal to 1. Now the 0 at minus 1 is of multiplicity 2 because of this exponent, and that means we will not expect a change of sign there, and that's in fact validated when we look below. We're going to be tangent to the x-axis. If you multiply all this stuff out, you have a 4th degree polynomial that has a coefficient of minus 1/2. That means it's going to be a frowning thing. If we put x to be 0, we will get a minus 2 here, we will get a 1 here, and we will get a minus 1 here. And if we multiply all these things together, we will get minus 1 for our answer. So the y-intercept will be there. Okay, so we will go from negative infinity up to minus 1, from minus 1 to 1, from 1 to 2, and from 2 to positive infinity. So those are how we parse the real number line. Test points in all of these intervals are selected to be easily computed, and I find out the values of the function at those test points, and I see that they're negative, positive, negative, and negative like we expected. So the graph is going to look like this. Again, we have the in behavior is a frown, we have a root here, we have a root here, and we have a root here. So those were the three roots we have. This is the double root, and that's why you see the tangency to the x-axis. And again, the y-intercept was 0, -1. The relative min is going to be near this point. The relative max is going to be near this point. And again, you find these using your calculators, as we've discussed before, from the left and from the right. And then you give a guess. And your calculator does all the heavy lifting with those. And here is filling out the paper again. Again, there were two relative maxes, one at -1 and the other near this point on our graph, and the only relative minimum happened there. This chapter also has you graphing piecewise functions. Now, we've done piecewise functions before, both for linear functions and for quadratic functions. So the only real new thing is that we're having a polynomial function involved in one of the domain segments. And here we're talking about x cubed -1. So again, I'm going to be asking you to pause the video, give it a go, and answer the questions that are in my prototype thing. I want you to graph it, talk about in behaviors, and so on and so forth. So please pause, and I will return. I'm back. And here's what your picture should look like. This is a discontinuous function because we have jumps here. So this is an open circle, this is a closed circle. This is an open circle, this is a closed circle. And this is what happens from 1 on. So the in behavior is a left-handed wave because it's going up like this and going down like that. So it's a left-handed wave. As they're facing you, it is discontinuous. Your graph should look like that. There are two x-intercepts at -1, 0, and 1, 0, and the y-intercept is at 0, -1. So let's look at the way we would fill out the table, and there's our end behavior, the y-intercept, and the two x-intercepts. The last topic that we're going to discuss is called the intermediate value theorem. And you know that polynomial functions are continuous from a previous section. We can draw them with never having to lift our piece of chalk, meaning that the graphs are unbroken. The domain of a polynomial function, unless restricted by additional statements, is from -infinity to infinity. And what the intermediate value theorem thing is talking about is, okay, so if you're going from a positive value of y to a negative value of y and never lift your pencil from the piece of paper, you have to cross the x-axis. So that means if this one is positive, p of a is positive, and p of b is negative, you must cross the x-axis between a and b. And that's the statement of the intermediate value theorem. I am going to read this along with you. So if you have any polynomial function with real coefficients, and p of a and p of b are of opposite signs, then there has to be a real zero between a and b. Now, this is a very valuable theorem, and in fact, this is what your calculator is doing when you tell it the left bound and the right bound. It's really looking at those because you're just picking those values that are to the left and to the right of a zero. So the signs are changing there. So this is actually what your calculator is doing the intermediate value theorem over and over again. But it is not foolproof because you cannot use the intermediate value theorem, cannot be used to determine whether there is or is not a real zero between a and b when they have the same sign. There might be real zeros, there might not be. So sometimes the intermediate value property does not yield a solution. So let's look at these problems where it says use the intermediate value theorem, determine if possible. And sometimes it's not going to be possible to determine whether the function has a real zero between a and b or not. And again, I'm assuming that you have done the pre-reading of this section, so that means that you should be in a good shape to pause and try to work a couple of these, and I'm going to suggest we're going to do a couple. Why don't you try 44? So please pause now. I'll be back soon. And now I am back. Let's look at my solution to number 44. Now, for number 44, it is a polynomial, so we know it's continuous, so the intermediate value property can be invoked. And they're asking us to compare the values of f of x at f of a and f of b, 1 and 2. When you do that, you find that at 1 it is negative minus 4, and at 2 it is positive 51. By the intermediate value property, that means that since the function changes signs between these two numbers, you can conclude there is at least one root in between them. Now, even though this problem didn't ask you to do this, I think it would be really good practice for you to find an approximation for this root using your calculator. And the answer you should find would be x is approximately 1.32945. Let's do another problem. I'm suggesting you try number 46 for this. So please pause, and I will be back soon with a solution. Give it a go. Okay, I am back. Let's see how you did. Now, when we evaluate the function at minus 3, we get 62. And when we evaluate the function at minus 2, we get 2. Well, you see, both of these are positive. So, without further investigation, we cannot draw a conclusion from this. And sometimes it's not possible to draw a conclusion strictly from the intermediate value theorem. And you can see that, in fact, in this case, there is not a 0 between the two from the graph. All right, so to conclude today's lecture then, remember time is precious. Each day must count. Do the math. It will make you strong. A couple of additional notes today. Even the young must be careful, so take care of you. And please stay in touch with me and Hoy during alternative delivery in the time of COVID, and that's actually COVID, not COVID-19. Sorry for the typo. Take care.